Good morning, good afternoon, or good evening. In today's webinar, I will be discussing how to design a gearbox to prevent premature failure and unplanned downtime. Although there are no simple answers to this issue, there are best practices that all gear designers should consider to prolong performance, minimize repair costs, and boost efficiency. This presentation will cover the important fundamentals of gear, bearing, shaft, and housing design, as well as discussion of gear quality and environment. I am Bill Hubiak, Director of Engineering of Specialty Components Group, and I'm responsible for the product development and lifecycle for 3 distinct brands, including Berg. Prior to coming to Specialty Components, I held product management and engineering management roles with the Rexnord Innovation Center, the Research and Development Division of Rexnord. I was involved with many new product developments, including Falk V-Class, Thomas XTSR coupling, and several self-lubricating bearing programs. I have over 20 years of experience with Rexnord and have established myself as a proven leader across all facets of product development. I earned my bachelor's degree from Winona State University in both chemical and mechanical engineering with a focus on polymer composite materials. Enough about me. Let's get into talking about gearbox design. We'll spend the next 30 minutes talking about how to design a gearbox. We'll start by discussing what key information you need to know up front in order to effectively begin the process. We will then get into more of the engineering aspects of the design, from gear type selection, bearing, shaft, and housing selection, and design, and review how the center distance tolerances will impact the backlash of the gear set. We'll also talk about how design has an impact on temperature and lubrication performance, and end reviewing gear quality testing. Application constraints are the single most important factor for determining the correct design. Ask yourself, why do you need a gear system? Are you concerned most with positioning? If so, how precisely does that position need to be held? Are you looking to magnify the torque? Are you trying to change the orientation of the shaft? How much power do you need to transfer? Some of the most important constraints to understand when designing are, what are the input and output torque? What speed do you have, either input or output? What envelope size and orientation will the gearbox be? And what is the allowable overall backlash of the system? Temperature and environmental considerations should also be identified to ensure your application has the correct lubrication and sealing methods. Next, know the duty cycle. How often, either on an hourly, daily, weekly, monthly cycle basis, will the system run? Is there a decibel rating you cannot exceed? These will be important factors to consider when choosing the types of gears within the assembly. Getting answers to these questions up front helps to make the design process that much easier. Berg manufactures many different types of gears for many different applications. These include straight spur gears, our strongest and most common type of gear. Next are helical gears, similar to the spur gears but quieter running. Bevel gears are used in many applications where the input and output shafts are not parallel. Finally, we have worm gear systems, which are primarily used for higher ratio reductions in relatively small package sizes. All of the gear types that Berg makes are also available with an anti-backlash feature, designed to significantly reduce, if not eliminate, the backlash in the system. Please note, it is very common for a gearbox to contain multiple types of gears within it. For example, a bevel set may be used to create a right angle orientation of the input and output shafts, while spur gears are used for torque multiplication. For each gear type, there are specific tools that can be used to determine the capability of the gear set. In the next slides, we will discuss some of the more critical aspects of gear design and the tools used for them. The table on the left of this slide gives general properties of the materials most commonly used in gear applications. Selecting the correct material is of critical importance, as is selecting the correct material combination. Choosing poorly here can result in high costs. For example, the material may have too high performance capability for the application. Or, in some cases, a seized gear set, where improperly mated materials cause actually welding between the gears as they slide. On the right is one of the many equations for calculating gear tooth strength, the Lewis gear strength formula. This formula is for straight spur gears. There are other tools for the different types of gears. This equation assumes that only one tooth is transmitting the load and is, essentially a simple cantilever. It does not account for the root fillet or other key aspects that may otherwise influence the design. That said, we like to use this tool as a quick way to help identify the pitch and width of a gear required to transmit a given force. Please note that this is based on force. If torque is given, it should be converted to force at the tooth using the diametral pitch. The design of a gear system also includes an analysis of the thermal performance. As the force is transmitted from one gear tooth to the other, there are multiple types of deflection and contact that occurs. For example, with a worm gear system, the worm slides against the worm wheel typically for one complete revolution of the worm. This sliding contact deflects the worm as well as the tooth of the worm gear, and there is friction throughout this contact. All of the stored energy is released in the form of heat into the gearbox. The lubrication will have a maximum temperature before either the oil breaks down or the oil drops out of the grease. It will be important to stay well below this. Additionally, each gear system should be rated for maximum torque and speed. Operation above specifications will violate the thermal model and cause premature failure. This heat needs to be balanced with what the gearbox housing is capable of emitting. The designer has many options, including orienting the gearbox to maximize free convection, adding cooling fins, or finding other methods to extract the heat. One area that we often see confusion is in the use of the AGMA Gear Quality levels. Many times this gets overspecified with the belief that a higher quality level will result in stronger gears or will eliminate backlash from a system. Care needs to be taken as costs can rise almost exponentially as gear quality is increased. Q14 and higher gears are typically only used in very high precision applications or as calibration artifacts for gear testing. These gears are precisely ground to shape in very controlled environments and are some of the most expensive gears available for that size. Q12 gears are used in applications where efficiency is of high concern. For example, wind turbine drives. The use of the Q12 gears helps to ensure that the maximum amount of input power is converted to electricity and that waste due to inefficiency is minimized. Q10 gears are a balance of precision and cost and are used in many industrial applications. All of the Berg catalog gears are produced to a Q10 standard except for those made from polymers. Q8 gears are the most common and are used in applications where torque transmission and cost are more important than precision. Typical automotive transmissions use Q8 gears. Last are the Q6 gears. These tend to be more of the injection molded or powdered metal gears. Still very capable of transmitting good amounts of torque, but cost is of primary importance in the design. Like a chain, a gear system is only as strong as its weakest link. That is, if you specify a Q12 gear for one part of the system for precision, but have Q8 gears throughout the rest, you are not likely to get the performance benefit you expect. It is important to look at the whole system to determine what quality level is needed. Once the gear set has been identified, the next step our engineers follow is to determine what shaft should be used to transmit power. The obvious parameters are identified. For example, what is the torque applied to the shaft, what supports exist to hold up the shaft, etc., as well as the not so obvious ones. Will there be keyways, or will items be press-fit onto the shaft? All of this information is then used for examining the shaft deflections, as well as the strength to determine what materials should be used and what safety factor will be applied. Next is the selection of bearings. The type of gear you are using will often drive you to choose a particular bearing type. For example, helical gears produce thrust loads, and the selected bearing will often need to react this. Once the type is identified, the bearing is sized based on radial and axial loads, as well as the envelope available for it to fit into. If a rolling element bearing is too large, Berg also offers a number of bushings that are capable of thrust and radial loading to ensure that you can stay within the package size requirements. Berg has a handy reference in the back of the catalog for inner and outer ring tolerances based on ABEC or ABEC rating of bearings to help you in the design process. Designing the housing itself is typically the last thing that is done. Key factors include the envelope size. How much room do you have in which to fit the gearbox? Are there areas that you need to avoid due to other components? Gearbox mounting. Will it be shaft mounted or base mounted? Do you need threaded holes that support the gearbox and react torque? How much precision is required in the actual gearbox placement? Center distance tolerance. How closely does the center distance need to be maintained for the desired backlash? What impact will material properties have on this? Gearbox sealing. Is the design adequate for the lubrication system needed? Will it keep the grease or oil in and any contaminants out? Environment. Will this be in an environment where corrosion can occur? How well protected will that gearbox need to be? From all of this information, you can then choose the appropriate material for the gearbox housing. Good engineering calculations will be important to ensure that the housing has sufficient strength to transmit the power required. As we discussed previously, in precise applications, backlash can be a critical parameter in the performance of the gear system. Backlash occurs due to teeth not making perfect contact and being able to move freely in the system. As the operating center distance increases, noting that operating center distance may not be the same as the designed center distance, the teeth have more clearance and hence backlash increases. However, while decreasing the operating center distance will have the opposite effect, that is, backlash will decrease, care needs to be taken to ensure that binding does not occur as the teeth bottom out. Given enough torque, this can either cause wear of both the tooth and root of the gear or fracture of the tooth. The tables on this slide are a reference for the impact of the center distance on backlash of a Q10C gear set with a 20-degree pressure angle, with inches being on the left and millimeters being on the right. As you can see, small changes can have large impacts on the backlash of the gear set. This is why, most often, the Berg engineering team works to evaluate a gear system instead of increasing gear quality. Many other parameters influence backlash and need to be addressed differently. If the center distance tolerance is too wide, no higher quality gear will resolve the backlash issue. When designing a gear system, here are some common practices for calculating center distance with given inputs. First, if you know the chordal tooth thickness of the gears and the pinion is fixed in place, the center distance at which the gears will mesh properly and meet the backlash requirement can be calculated. Alternately, if you know the center distance and tolerance, the chordal tooth thickness of the gears can be calculated. This can be compared to the AGMA quality information to select the appropriate gears for the system. Next, we will discuss how the design parameters can influence the temperature and lubrication of the gear system. This discussion will assume that the appropriate materials have been chosen and that the gearbox has been adequately rated for thermal performance. The latter is another key parameter, ensuring that the heat generated within the gearbox will be sufficiently transferred to the environment so that the maximum temperature of the gear set is not exceeded. Improper alignment of the gears and related components can result in distortion of the gear teeth. As the gear teeth come out of mesh, this energy is released in the form of heat, much of which would not be accounted for in the design process. This can add up quickly. The Berg engineering team has helped many customers realize that even small misalignment issues can result in big thermal problems. Going back to the application constraints, it is critical to identify as much as possible regarding the operating environment of the gearbox. Items such as motor fans and other sources of air movement can significantly help performance. However, some common polymeric coatings that can give significant corrosion protection can also act as a blanket and restrict the flow of heat. Review this information and results of this carefully. It will be of critical importance. Much like for temperature, improper alignment can have significant negative effects on the performance of lubrication in the gearbox. Misalignment can cause the contact area to exceed the maximum force the hydrodynamic lubrication layer can support. This can result in direct metal-to-metal contact and, as you would expect, significantly accelerated wear. Gear tooth accuracy, more specifically the roughness of the tooth surface, also has an impact on lubricant performance. Too rough a surface will allow metal-to-metal contact, while too smooth a surface can add significant cost. A happy balance needs to be found to get the correct amount of performance for the targeted cost. Load, speed, and expected operating temperatures are the three factors that are used for selecting lubricants. There are many good resources for selecting on both the internet and with your local lubricant distributor. Please leverage these resources to ensure you use the appropriate lubricant. Once the lubricant is chosen, the designer must decide on how to ensure that it is present on the gear faces when contact is made. For lightly loaded, low-speed systems, a light coating of grease during assembly may prove to be enough. Because the system is moving slowly, the grease is not likely to be flung off the teeth. Additionally, because it is lightly loaded, degradation of the grease may take a longer period of time. Care will need to be taken to ensure that the thermal capacity of the system, including the lubricant, is not exceeded. For high-speed or highly loaded systems, an oil bath may be the preferred solution. This system will have higher thermal capacity because the oil will be in contact with the gearbox housing and can conduct heat away more easily. However, churning of the gears through the oil will take additional power and generate more heat. The oil bath may also require a change following the run-in period or through a regular schedule. One of the critical items to ensuring gear system performance is quality control throughout the gear making process. For the next couple of slides, we will discuss how Berg ensures the quality of the gears is maintained using the double flank test method, a process that has proven very reliable over the 50 years Berg has been manufacturing gears. In order for both our operations and quality team to know what they are testing, a setup sheet is completed for each production lot. Information regarding both the gear being produced as well as the master gear that will be used is entered into the data sheet. One key piece of information that is needed but many times overlooked is the arbor size, chosen to accommodate the bore size and allow the gear to be mounted, but tight enough tolerance to not affect the results. We talked before about the high cost of AGMA Quality 12 and higher gears. The master gear is one of the drivers of this cost. In order to ensure an accurate test, the master must be of higher quality than the gear that is being produced. Once the setup information has been collected, the tests are performed. From this data, we look for the results from two critical factors. Both of these types of error are considered test radius errors that are shown when doing composite testing on the test rig against a master. Total composite error is the difference of the highest center distance and the lowest center distance over one complete revolution of the gear. And tooth-to-tooth error is the largest deviation of any single tooth, that is, crest to the adjacent root on the graph. These are important to the designer because AGMA defines these two measurements as the readings necessary to give a quality rating with this testing method. The theory is that a perfectly formed tooth will show no center distance deviation. Therefore, this test accounts for profile, pitch, lead, tooth thickness, and total runout. Today we have addressed the issue of premature gear failure resulting in unplanned downtime. We have established that gear design choices early in the development process, along with preventative maintenance care, can extend the operating life of any gear drive system. We have stressed that application constraints are the single most important factor in determining the correct design, and that you must consider torque, shaft orientation, the transfer of power, and the environment to produce a gear drive with a long lifespan. We have called out AGMA Gear Quality Standards to help you determine the correct quality specs for an intended application, along with shaft and bearing design. In order to help you better determine how to design a gear system, we have provided a copy of the Berg Gear Specification program with the materials from this webinar. This program will calculate the gear data necessary to manufacture fine pitch external spur gears, internal spur gears, helical gears, worm gears, and worms. It will calculate diametral pitch ranging from 12 to 120 per inch and from 0.25 to 1.5 module metric series. You'll be able to factor in gear specifications based on AGMA standards for both inch and metric. These specifications calculate data based on backlash classes ranging from A to E, gear quality from Q5 to Q14, and metric to inch calculations if desired. All of this information is then available for you to print or copy into your drawing. We hope this seminar gave you some guidance on how to design gear drives to perform better and last longer. please let me know if I can provide further information like application notes or technical information sheets that may help you gain a deeper understanding of the various gear spec requirements and how to configure them accurately. At this time, I will answer some of the questions that have been submitted as this webinar has been presented.
Okay, Bill, thanks very much for that great presentation. Right now, we do have some questions for you that came in from our attendees, but before we get to them, let's just remind everyone that if we don't get to their question, they can just submit them in the Q&A box, and rest assured, you will receive an answer by email. Okay, let's take a look at those questions, Bill. Here's your first one. What is the most important thing someone should take into consideration when designing a gear drive?
The most important thing I've coached my team to take into consideration when designing a gear drive is to get all of the application information up front. Designing without this usually leads us to at least one rework loop, and this of course adds time to the project. Getting all of this information up front ensures that you can address all of the issues throughout the design process so that the end product meets the requirements of the application.
Okay, Bill, thanks for that answer. Here's another question. How can you reduce backlash in a system?
As we discussed in the presentation, one of the key factors is to look at this from a system design. So if you've got a gearbox that's already designed, you've got a undesirable backlash in the system, how do you go back and figure out what to do to eliminate that? So look at it from a system design, what exactly could be contributing to that. Center distance tolerance is one of the areas that we generally focus in on, making sure that the center distance tolerances are aligned with what our expectations are and that they actually were manufactured. So using a CMM or some other precise tools to measure them. If that looks to be in line, we'll evaluate higher quality gears to see if tightening up those tolerances will reduce the backlash, or in other cases we'll actually move to going with an anti-backlash gear, which will all but eliminate the backlash in the system.
Okay, great. Thank you again for that answer. Let's take a look at another question. What tooth modifications can be made to help performance?
First, I want to ask everybody to use caution when looking at tooth modifications. They can be very expensive, and if you don't truly know what you're doing, it can lead to a lot of cost and not a big performance benefit. The cost is driven a lot by that when you get outside of the standards, there'll be custom tooling required, and there'll also be a custom master gear that's required for the testing, and those can add up pretty quickly. One of the common changes, or one of the common areas that we do experiment with, is around pressure angles, trying to dial that in for specific customer applications. For example, you can change from a 20-degree pressure angle to a 14.5-degree pressure angle, which will result in actually lower bearing forces because the angle of the force changes, but also weakens the tooth of the gear by at least 10%.
Okay, Bill, and thanks again for that answer. This next attendee looks like they have a two-part question. How does the AGMA quality level affect strength, and does it affect accuracy?
AGMA quality level, it does affect strength and accuracy by tightening up the tooth profile tolerances. And then it also, because of those tighter tolerances, reduces the amount of what we'll call, quote unquote, imperfections that are on that tooth surface. Because these imperfections are reduced, they actually will strengthen the tooth because they no longer act as a stress concentration location on the tooth face. Likewise for accuracy, the increased precision of the gear tooth profile can decrease backlash simply because of the smaller tolerance that the tooth profile is allowed to have.
And thanks again for that answer, Bill. We've got time for another question. Let's take a look. How does material selection impact strength or the performance of the gear system?
As we saw before in the Lewis gear calculation, the selected material will have a direct impact on the calculated tooth strength of the gear. Ensuring that this is done correctly will make certain that the gears have enough strength. That said, especially in helical and worm systems with sliding contact, The material choice also needs to be looked at as a system to ensure that you don't get galling between the two surfaces as they slide against each other, or some of the other phenomena that can occur during sliding of metal on metal components.
Okay, Bill, thank you very much for those answers. Right now, we're going to have to wrap up this webinar right there. That's about all the time we have for questions. So thanks for joining us today, and a special thanks to all of our audience members for being part of this webinar event. And remember, if you submitted a question, Bill will get back to you via email. Again, thanks for taking the time to join us for this webinar event. Take care and have yourselves a great day.